So right now you're probably saying, Miss P, you're really nice, but what the heck are you talking about? All right, well, let's look through an example, and I think all of what I've been saying about electron configuration will make sense. Write the electron configuration for K. And K, of course, is potassium. And so to write an electron configuration, we need to know how many electrons we're dealing with. So we find potassium on the periodic table. Its atomic number is 19, so that means there are 19 electrons. Now what we have to do is take these 19 electrons and put them in the correct energy levels and subshells, and we do that from lowest to highest. And here is our super duper diagram that shows us how to do it. So I have 19 electrons, but I'm going to put as many as I can in this lowest energy level and subshell, which is 1s. Now we know that the s subshell can only hold 2. So we put how many electrons there are as a superscript. Now this is full, so I've got to go on to the next one. So go all around. Here's my next one, 2s. Now I know my s subshell can only hold 2 electrons, and I have 19 total that I have to account for. So this takes care of 4 of my 19. I have 15 more to go. So after my 2s, go around and I go to my 2p. 2p can hold 6. So now I have 10 electrons, 9 more to go. After my 2p comes my 3s. I know that can hold a maximum of 2. Alright, so I have 12 electrons. Got to keep on going. After the 3s comes my 3p. And that can hold a maximum of 6. So I now have 18 electrons. I have 1 more electron to go. Where does it go? After my 3p comes my 4s. And even though the s can hold a maximum of 2, I don't have 2, I only have 1 more. And so I put 1 electron there. And if I count my number of electrons that I have as subscripts, it'll equal 19. And my diagram told me the order that I needed to place my electrons in, and I knew that S subshells can hold 2, P subshells can hold 6, and that allowed me to put the correct number in. We've got to fill each subshell up before we go to the next one. So why don't you try and do one on your own? How about if you write the electron configuration? Let's see. How about zinc? So pause the slide and see if you can get it. So the first thing you want to do is check your periodic table to see how many electrons zinc has. Here's zinc. It has an atomic number of 30, so the atom has 30 electrons. And then we just use our handy dandy chart to let us know where those electrons go. We always start with 1s, then our 2s, then our 2p, then our 3s, then our 3p, then our 4s. And that's as far as we got with our potassium. But if we look back now after 4s, where do we go? We have to come back around and go to 3d. So 3d is going to be my next energy level and subshell. And let's see how many electrons I have. 10, 16, or 18, 20. So I have 20, so I have 10 more to go. And my D can hold 10. So that's great. I totally fill up my D subshell. And so if you've got this as the electron configuration for zinc, you are doing great. Now, one thing that we need to know when we are putting these electrons in an orbital, we know that orbitals can hold, each orbital holds a maximum of 2 electrons. There's something known as the Pauli exclusion principle that says that any 2 electrons in a given atom must have 4 different quantum numbers. And what that boils down to is any electrons in one orbital must have spin up and spin down. So what, again, the heck am I talking about? Well, electrons actually have what's known as a spin. They have an axis that they spin around. And when they do this, they generate their own magnetic field. When two electrons are in the same exact orbital, their spins are opposite and their magnetic fields cancel out. So the way that we represent spins is by an up arrow or a down arrow. This has one spin, this has the opposite spin. We often just say spin up and spin down. Now, this is what's known as an orbital diagram. It's related to electron configurations, but it's more detailed. Instead of actually writing just the energy level in the subshell, we write boxes or circles or lines that indicate our orbitals. And this would be an unoccupied orbital, an orbital that has no electrons in it. This would be an orbital with one electron in it. We always place it with spin up. And then this would be an orbital with two electrons in it, spin up and spin down. Now let's look at the relationship between electron configurations and the orbital diagram. Here's lithium, which has an atomic number of 3, so it has 3 electrons. Here's its electron configuration, and this is what its orbital diagram would look like. We go from left to right the same way that we do with our electron configuration, and then each orbital is represented by a box. We fill our 1s before going to the 2s, so it's spin up and spin down. And then our last electron is unpaired and spin up. Here's beryllium, 4 electrons, 1s2, 2s2. The 2 electrons in the 1s orbital are opposite spins as they are for the 2s. Here's boron with 5. Its electrons in the s orbitals are opposite spins, and then here we have 1 electron in our p orbital, goes up. Now, if we're looking at a given subshell, such as the 2p subshell or the 3d or any subshell, electrons have negative charges and repel one another. So if possible, they want to be as far apart as they can be from one another. And all the orbitals in a given subshell have the same energy. So this p orbital, and this p orbital are all part of the 2p subshell. They all have the same energy. And these electrons, rather than being close to one another and pair up, want to be as far apart as possible. This is what's known as Hund's rule. When you're filling up subshells with more than one orbital, so the p, the d, or the f, you keep electrons unpaired as long as possible.